Hey guys, welcome to my channel. My name is Lokesh. I work as lead architect, lead data and AI architect in one of the organizations called Fractal Analytics. So in this video, we'll again continue our book reading series. We are covering chapter one of a book called LLM Engineer's Handbook, which is available in O'Reilly. So if you are interested, to read the entire book, I would consider you to subscribe to O'Reilly, platform, or you can purchase the book uh, from any of the websites that are available. So let's continue this. So in today's video, we'll go over the technical architecture for designing or developing LLM Twin. So far, in terms of recap, we have gone through what is LLM Twin, why do we need it, what are some of the old ways of architecting an ML application, what is FTE architecture, which is the latest decoupled architecture where you can have different pipelines you know developed and deployed on different machines, and the concept of reusability comes into picture. So today we'll go through the LLM twin architecture. So as I have said in the previous videos, this is like learning on the fly, studying on the fly. So I would read the book maybe as quickly as I can, or maybe sometimes I might not be able to, you know, read it loud. But while I'm explaining, I try to, make sure that I explain the things correctly and clearly. And if you have any questions, please ask in the comment box below. And if you have any suggestions, please, consider them adding in the comments box below. So with that said, let's dive into the topic for this video. So let's look into this. So the title said designing the system architecture of the LLM Twin. In this section, we'll list the concrete technical details of the LLM Twin application and understand how we solve them by designing our. Before diving into, we want to highlight that we won't focus on the tooling or the tech aspect of this. We only want to define a high-level architecture of the system, which is language, framework, platform, infrastructure agnostic. We will focus on each component scope, interface, and interconnectivity. In future chapters, we'll cover the implementation details and tech stacks. That makes sense. That is mostly self self-explanatory. Listing the technical details of the LLM Twin architecture. Until now, we defined what the LLM Twin should support from user's point of view. Now, let's clarify the requirements of the ML system from a purely technical perspective. So, on the data side, we have to do the following. So, let's do a brainstorming exercise before even looking into the LLM Twin architecture. Let's from the knowledge that we have try to define a very high level architecture. So this would require some sort of brainstorming, and this would need some sort of drawing board. So let's do that. So here we have the whiteboard. So let's brainstorm and try to define the high level architecture of LLM Twin. So LLM Twin, is, as we have seen in the previous videos, is a way. It's like an AI, avatar or a AI character that will try to mimic our writing style. Now it will not be able to do everything, autonomously. That is, it would need some, inputs from us, because if it is able to, if it does everything autonomously, then things can go haywire, and we might run into issues because there would be things that would be posted on some of the social media websites, which we don't want that. So I think what it needs is a UI. So there should be, I'm sorry for this, let me just get the drawing option. So first of all, it would need a UI. Okay, so UI, I think it would be similar to what most of the chat GPT or chat applications are as far as Gen AI is concerned. there would be some way wherein we can type in the prompt and then it gives us the output. It would be interesting to know here is what sort of prompt we'll provide, because sometimes the prompt should be as good as writing the content on the social media website, but maybe we are concerned about the post which could be longer, which requires some sort of reasoning thinking, and it should be grammatically correct as well. So that is why maybe we would need the output, a lengthy output from the UI. So this is UI. Now it will also need some data, obviously. So and the data should be stored and encoded in a vector DB, because if it doesn't have any data, then how this application would know or would try to infer the writing pattern that I has, or if you're designing it yourself, you have. So it needs to have some sort of data. This data could be drawn from the websites. It would be interesting to know whether we could do that or not. So, for instance, I write a lot of things on LinkedIn, so maybe it is able to draw it from there. I've also written some blogs, so maybe it would be able to, we'll be able to get that data. And having data is important, but that data has to be encoded in and stored into a vector DB, because when a prompt is sent, or a question is sent to the LLM, uh, not only with it, not only the content of the question asked would be sent to the LLM, but also the LLM would be asked to get the data from this vector DB. So you need to have one LLM, and I think we'll mostly be using API calls for this. So how this would work is you write in the prompt first, and that prompt, along with the data that would be here in the vector DB, would then go into the LLM. And LLM, what it would do is it would just do the text generation. So even though this LLM models, some of these LLM models, I'm not talking about the reasoning models, I'm talking about the simple models. These are simple text generation models, or auto completion models. So there would be some algorithm based on that it will be able to produce the output, but it will be only be looking up, as far as I know in this case, it would only look up the data that we have here and not the data from internet maybe. But then the question comes, if I have not written a post on a specific matter or a domain, how it would get the data? Or maybe whatever I'm just talking about is a case of a RAG application, but LLM Twin maybe uh, have a different architecture. But one thing is for sure, need to have one UI. So this UI could be hosted on a web app. I come from Azure, background, so I'm just trying to have it here, web app, and these calls would be made through API. Also, the request would be also received through ABI. We need to have a vector DB, and then we also need to collect the data. So these are some of the columns. And how do we orchestrate all of this? Is that would be through a custom, code which could be written in Python. So maybe this is something that would be there. Let's see how close are we as compared to the content of the book, and how close are we will also depend on what we think the LLM twin should do. We think that the LLM twin should be able to provide you the UI, and you should be able to write in the prompt and get the replies in terms of a post that you can copy the content and put it into any of the social media websites such as LinkedIn or any other website. So yeah, let's continue that, and let's now look into the content from the book. Now let's look at the architecture details from the book. Until now, we defined what the LLM twin should support from user's point of view. Now let's clarify the requirements for the ML system from a purely technical perspective. So this is good. They are defining the requirements clearly. On the data side, we have to do the following tasks. Collect data from LinkedIn, Medium, Substack, and GitHub completely autonomously and on a schedule. Okay. Standardize the crawled data and store it in a data warehouse. Clean the raw data. Create instructs datasets for fine-tuning an LLM. Chunk and embed the clean data. Store the vectorized data into a vector DB for RAG. Some of the things that we couldn't envision was cleaning the data or maybe, instruct data sets for fine tuning. We were not thinking that we'll have to, fine tune the LLM, but this is an important part. This we guessed that we would need a RAG, we would need a vector DB. So for building RAG, because whenever your data comes into picture, when you try to communicate with LLM and try to find the answers, that is where, retrieval augmented, I think, yeah, retrieval augmented something, right? Getting relevant content. RAG is a technique combines strength. Retrieval augmented generation. Okay, where did it go? Okay, for training, we have to do the following: fine tune LLMs of various sizes, fine tune on instruction datasets of multiple sizes, switch between LLM types, for instance, between Mistral, Llama, and GPT. So they're saying they would be using a variety of LLMs, okay, which is interesting, and with a variety of LLMs, and that too from different providers like Mistral, Llama, and GPT. Track and compare experiments, test potential production LLM candidates before deploying them, automatically start the training when new instruction datasets are available. Test potential production LLM, okay, before. Track and compare experiments, test potential production LLM candidates before deploying them. Okay, so they would try to test on these models, and whichever suits the best, or maybe ranks higher, would be selected. Automatically start the training when new instruction datasets are available. The inference code will have the following properties: a REST API interface for clients to interact with the LLM twin, access to the vector DB in real time for RAG, inference with LLMs for various sizes, auto scaling based on user inputs, automatically deploy the LLMs that pass the evaluation steps. The system will support the following LLM ops features: instruction dataset versioning, lineage and reusability, model versioning, lineage and reusability, experiment tracking, continuous training, continuous iteration, continuous delivery, prompt and system monitoring. So if I were to summarize that means that you need data, and you need some data that could be used for fine-tuning LLM, and then cleaning is also required. For training, obviously you would need some LLMs, and there should be ways, whatever tools you should have, you have at your disposal. You should be able to, that you should be able to have the capability of switching between different LLMs and conducting operations. And then you should be able to, so after you conducted the experiments, one of the LLMs might outperform the others, and you should be able to automatically deploy it to production. The inference code will have the custom properties. A REST API interface for clients to interact with. So whatever we are going to build will have a REST API, access to the vector DB in real time for RAG. Okay, this we discussed. Inference with LLMs for various sizes. Inference of L with LLMs of various sizes. So this is the custom code. So custom code should be able to read the output from LLMs, maybe auto scaling based on user requests. So our code should be in a way that it should be able to handle, larger requests, automatically deploy the LLMs that pass the evaluation step. Then the system will support the following LLM ops feature: instruction dataset versioning. So there should be versioning for the dataset for the models. Then there should be way to track the experiments, and then there would be, CI/CD for continuous training, integration, and delivery. The preceding list is quite comprehensive. We could have detailed it even more, but at this point, we want to focus on the core functionality. When implementing each component, we will have to look into all the little details. But for now, the fundamental question, okay, that makes sense. How to design the LLM Twin architecture using the FTI design pipeline. So up till now, this was the build-up for FTI architecture. The meat of the this topic would now start. It's very good to gradually dive into the topic. You should need to understand why the things are being done and what are the tools, especially in this case when the technology is new. You should be able to understand the terminologies. How to design the LLM twin architecture using the FTI pipeline design. We will split the system into four components. You will ask yourself this four, why not three? Yeah, that's a genuine question. Fortunately, the answer is simple. We must also implement the data pipeline along with, okay, got it. Data pipeline is also important because it should be able to automatically collect the data and put it into the right space so that the subsequent pipelines can pick it up. The data engineering teams owns the data pipeline. The ML engineering teams owns the FTI pipelines. This is a very good, distinction, especially, if I try to give you an example. Right now, I'm part of data engineering team within my current organization. So sometimes this question comes in: what would be the job of a data engineering team, and what would be the job of a ML engineering team? So I understand some of the tasks would be overlapping, and whenever engineering tasks come to data engineering tasks, first of all, they might not know it, and that is a good practice to draw a line on that. But who will draw the line? So if you don't understand all these architectures, you might not be able to draw the line. But this is an important thing that I found here. Let's continue. So given our goal of building an MVP, minimum viable product, with a small team, we must implement the entire application. This includes defining the data collection and FDI pipelines. Tackling a problem end-to-end is often encountered in startups but that can't afford dedicated teams. Thus, engineers who have to wear many hats depending on the state of the product. Yeah, that is precisely what I talked about in smaller teams. So, in my current organization, we have the luxury of dividing, having different teams. But what if you only have one set of engineering teams? So they would have to do both of these tasks. Nevertheless, in any scenario, knowing how an end-to-end ML system works is valuable for better understanding other people's work. Figure shows system architecture. The best way to understand is to review four components individually and explain how they work. So you have a data collection pipeline. So this is a typical pipeline where you try to collect data from different sources. So here we are talking about social media or blogging sources. Then you put it into a NoSQL DB. That is correct because you will be dealing with posts, blogs, which is not a structured data. So you have to store it into a NoSQL DB. Then comes your feature pipeline, you will have articles, posts, code, and then you put it into a vector DB, logical feature store, retrieval client, then it goes into instruct data set, fine-tuning data, then training pipeline, LLM fine-tuning, experiment tracker, test LLM candidate, LLM production candidate. It goes into model registry, and then you deploy it. This is inference pipeline, write a post about. Then you'll have REST APIs, retrieval client, LLM Twin, and then prompt and system monitoring, and then generated post. So you have data collection pipeline here. Here you have a feature pipeline. So the type of content that you write on media, social media, and blogs could be classified into three categories: articles, posts, code. You'll have sometimes when you're writing or explaining the things, especially in the Medium articles or maybe in the LinkedIn articles or in GitHub, you'll have a lot of source code. That is where this third category comes into picture. Then you store this into a vector DB. I didn't understand this retrieval client and instruct data set. Then this data is used to train or fine-tune LLM. Remember, guys, we are fine-tuning it. We are not pre-tuning it, pre or training it. Training LLMs are already trained, but you just have to fine-tune it based on the data you're dealing with, experiment tracking. By the way, I can think of this architecture pattern as a mixture of fine-tuning as well as RAG, because I have studied that people use RAG systems just to avoid fine-tuning their LLMs. Maybe I might be wrong, but let me just Gemini this. We'll just write difference between LLM fine tuning and RAG. Let's see what it spits out. Um, Let it explain. We will be looking into the table. Modifies model parameters, connects to external sources, label data access to relevant data sources, computational cost high. These are two different, architecture patterns. LLM fine-tuning is costly, transparency limited, high use cases, specific task domain, knowledge intensive tasks. So what I've learned so far is that you can either go with LLM fine-tuning or you can have a RAG system. But in this architecture, if you see, you have the fine-tuning also, and then you have the RAG component 2, or maybe RAG is not here. Yeah, you have this RAG data, right? Or maybe they're calling the data as RAG data, but this architecture-wise, this is not a RAG architecture, so this could be a possibility. So then we look into each of the pipelines and we'll see how that works out. So let's look into the data collection pipeline. So the data collection pipelines involves crawling your personal data from Medium, Substack, LinkedIn, and GitHub. As a data pipeline, we will use the extract, load, transform pattern to extract data from social media platforms, standardize it, and load it into a data warehouse. So remember, guys, there are two patterns. One is ELT and the other one is ETL. ELT is you extract, then you load, and then transform. But this is ETL, you extract, then extract, load, transform. I think they should have written it here as extract ELT. So this is ELT pattern.
Extract, transform, load is where you deal with structured data. So you extract the data, you put or do some transformations on top of it. Maybe you want to clean the data, maybe you want to get rid of redundant data, duplicate data, or you may want to add some calculated columns. So that is where your ETL comes into picture. But this is ELT. You first extract, then load the data, and then you try to and then load it into extract. That's misleading because you can see here they're mentioned as a data pipeline. We will use the extract load transform. So which is ELT, pattern to extract data from, standardize it, and load it. That's okay. It is critical to highlight that the data collection pipeline is designed to crawl data only from your social media platform. It will not have access to other people. As an example for this book, we agreed to make our collected data available for learning purposes. Otherwise, using other people's data without their consent is not moral and not legal as well. The output of this component will be a NoSQL DB, which will act as our data warehouse. As we work with text data, which is naturally unstructured, a NoSQL DB fits like a glove. So this is something we have already discussed. Even though a NoSQL DB such as MongoDB is not labeled as a data warehouse from our point of view, it will act as one. Yeah, this was the the concern that I had, or that was conflict in my mind. Why are they calling this as data warehouse? Usually, when you store unstructured data, you'll not call it as a data warehouse. Why? Because usually the data warehouse by concept should be able to give insights about the data. You should be able to fire SQL queries or build dashboards on top of it. But warehouse is a warehouse. You keep your things over there, so that's why they're calling it data warehouse, because it stores standardized raw gathered data by various ETL pipelines that are ready to be ingested into an ML system. The collected digital data is binned into three categories: articles, posts, code. We want to extract any platform where the data was crawled, for example, when feeding article. So this is self-explanatory. I'm not going to read through these two, paragraphs. So there could be three categories of data that we have collected. We have already discussed about this. Articles, mostly Medium, Substack will have articles, although LinkedIn could also have articles. But mostly, people use LinkedIn for doing short snippets, which are called posts. And then you have code, which is mostly will be in GitHub. Cool. That explains our data pipeline. So let's move into the feature pipeline. The feature pipeline's role is to take raw articles, posts, and code data points from the data warehouse, process them, and load them into the features store. The characteristics of the FTI pattern are already present. Here are some custom properties of the LLM Twin's feature pipeline. It proposes three types of data differently. Processes rather, not proposes. Articles, posts, and code. It contains three main processing steps necessary for fine-tuning and RAG: cleaning, chunking, and embedding. It creates two snapshots of the digital data, one after cleaning, used for fine-tuning, and one after embedding, used for RAG. It uses a logical feature stores instead of a specialized feature store. Okay, so once you have collected the data and you are storing it in NoSQL, so-called data warehouse, from there this feature pipeline will pick up the data, and you will have two versions of the data. So they're calling it as snapshots. One is once you clean the data, you get rid of redundant data, so that would be used for fine tuning. And the other one is the embedded data, so that would be used for RAG, specifically used for uh, embedding into a RAG vector DB. Let's zoom in on the logical feature store part a bit. As with any RAG system, one of the central pieces of the infrastructure is a vector DB. Instead of integrating another DB, more concretely a specialized feature store. We use the vector DB plus some additional logic to check all the properties of a feature store our system needs. The vector DB doesn't offer the concept of a training dataset, but it can be used as a NoSQL DB. This means we can access data points using their ID and collection name. Thus, we can easily query the vector DB for new data points without any vector search logic. Ultimately, we'll wrap the retrieved data into a versioned, tracked, and shareable artifact. For now, you must know it is a it is an MLOps concept used to wrap data in addition with properties listed before. How we will use the rest of the system accesses the logical. Okay, so we need to go through this two paragraphs because I haven't quite understood the meaning of it. Logical feature store part a bit. So let's look at the architecture here. Where is the logical feature store? So this is the logical feature store. So they are storing all of their data into vector DB. So you have a NoSQL DB, you have vector DB. Okay. As with any RAG-based system, one of the central pieces of the infrastructure is vector DB understood. Instead of integrating another DB, a specialized feature store, we use the vector DB plus some additional logic to check all the properties of a feature store our system needs. So one of the important questions here is feature store essentially is a store, which means you're storing something, which means it needs a database. So let me first try to find out how feature store is implemented. How feature store is implemented. Yeah, that should be all. Implementing a feature store involves several key components: data ingestion, data feature engineering. We are we're mostly looking into feature storage, online store, user load, Redis Cassandra to store the latest, or offline use a scalable data warehouse like choose an appropriate data model such as annotated centric. There are varieties of ways in which you can store the data. You can have it in online store, offline store, data model. Okay. I think what they're trying to do here is instead of using a separate database for storing features, they are using the vector DB itself. So you can see here from the sentence, instead of integrating another DB more concretely, a specialized feature store, we use the vector DB plus some additional logic to check all the properties of a feature store our system needs. The vector DB doesn't offer the concept of a training data set, but it can be used as a NoSQL DB. This means we can access data points using their ID and collection name. Thus, we can easily query the vector DB for new data points without any vector search logic. Ultimately, we will wrap the retrieved data into a versioned, tracked, and shareable artifact. For now, you must know it is an MLOps concept used to wrap data in additional properties listed before. So storing is one thing. So they're saying that vector DB doesn't necessarily store data, training data that could be used for fine-tuning LLM. You can access data points using it. So you can, save the data and in a format of ID and collection name, just like we do it in, some of the NoSQL DBs like Cosmos DB. Thus, we can easily query the vector DB for new data points without any data vector search logic. So usually in vector search, you would be trying to, search the embedded text or encoded text. So why they are saying that query the for new data points, we don't need a vector search logic. Yes, that's right that you can query the data based on ID, because if it's a new ID, that means that's new data point. But why they are comparing it with a vector search logic? Let me just type something here. If we are using vector DB for storing features, then why we won't need to perform vector search, and we could and instead we could use ID for accessing referring to new data points. So let's see what answer we got. You write to question that it seems counterintuitive that you would use a vector DB and not leverage its vector search capability. Here's why you might use an ID for accessing new data points. ID is provide a unique identifier for allowing for quick and efficient retrieval. Think of it like primary key metadata, so you might store additional metadata. Operating a why you still need vectors if finding similar data is to find similar data points relationship. Okay, so I think we'll have to understand what we are trying to do when we build an LLM twin. So the way a vector search comes into picture is, especially in RAG systems, the method in which how I understood is that, let's say you have some documents, and in one of the documents you have used a sentence called uh, my last job consisted of writing code as well as designing architect diagrams. But if you're using a RAG system and if you're using a prompt or giving a prompt saying that find out all the material where you have written that or maybe find out all the jobs where you did coding, or find the let me take a step back. The prompt is give me the all the jobs where you wrote source code. So now coding and code might be slightly different, uh, but they could be a better example of it. Maybe I'm not able to find out. Maybe the prompt is find all the jobs where you had you did hands-on, uh, and you wrote hands-on and you wrote Python, for example. Let's say Python. What is Python used for? It is used for coding. So there would be linkage between Python and coding. And if you don't have vector search, which means it will not be able to find out the similar words by using some of the encoding. you'll not get the answer. I still think that in this architecture there will be vector search, but maybe when it comes to feature store or finding out new data points, you might not need it, and that's why you're using ID for that. But we'll soon find out. So let's continue. This means we can access data points. So for now, okay, that's okay. How will the rest of the system accesses the logical feature store? The training pipeline will use the instruct datasets as artifacts, and the inference pipeline will query the vector DB for additional context using vector search techniques. Oh, here you go, mate. For our use case, this is more than enough because of the following reasons. The artifacts work great for offline use cases such as training. The vector DB is built for online access, which we require for interface. The training pipeline will use the instruct datasets as artifacts. So one of the other things which was not clear was what is this instruct dataset? Because it appears that this is also one of the DBs. So why do we need it? How will the rest of the system access the logical features store? The training pipeline will use the instruct datasets as artifacts, and the inference pipeline will query the vector DB for additional context using. For our use case, in future chapters, however, we will explain how the three data categories are clean, chunked, and embedded. To conclude, we take in raw article, post, and code, process them, and store them in a feature store to make them accessible to the training and inference pipelines. Note that, oh, maybe instruct. This is where you are storing your feature. Retrieval client instruct. It's still not clear. Let me just try to take a stab and try to find out the meaning of this part. So I'll just snapshot. I'll just take a snippet of this, and then we'll save it, and then we'll go into the Gemini. We'll upload an image, put it here. What is instruct data instruct? Is it data instruct? Instruct data set in this image. Maybe I think it might not be able to return an answer, but let's see. Or if a data set specially defined instructing. These are prompts or commands given to LLM, guiding it to perform. This is how it works. Training is a vital role in training the LLM to be more responsive and accurate in following instructions. By providing a diverse range of instructions and their corresponding outputs, it helps the LLM how to generalize to new and unseen tasks. Is used to fine-tune the LLM, enabling it to better understand and respond to instructions. Instruct dataset. So you have a vector, you then have a retrieval client. Maybe then what is retrieval client? Retrieval client in that image is crucial component that bridges the gap between user's input and receiver receives user input. This could be a question. Process the end converts into a format suitable for querying the vector. This often involves text embedding, tracks with vector data, retrieves relevant results to LLM. Think of the retrieval client as a specialized library that when the user's request it knows how to navigate the library, retrieves the most relevant, and delivers those to the reader. Fine-tuning data. Hmm. So you have a retrieval client. So by looks of it, retrieval client would only be invoked when you type in the prompt. So how are you then fine-tuning LLM? Fine-tuning data. So maybe this retrieval client would be kicked in or would be triggered when you try to ask a question or ask a prompt, but usually in the instruct data set, let's say the system has not gone live and is still fine-tuning it. So you'll have a set of instructions here, maybe some of the prompts that you think the people are going to ask. And then along with that, you'll have features here, and then you will pass it to LLM fine-tuning. To conclude, we take in the raw code, store them features store to make accessible to training and inference pipelines. Note that trimming all the complexity away and focusing only on the interface is perfect match with the FTI pattern. Beautiful, right? Don't know whether it is beautiful or not, but we are struck we are we are stuck with instruct dataset. How will the rest of the system access the logical feature store? The training pipeline will use the instruct datasets as artifacts, and the inference pipeline will query the data. So some features along with some of the prompts would be stored in here, and that would be passed to LLM. There would be some experiment tracker. So maybe things will be more clear, as we look into some of the other pipelines like training pipeline and inference pipeline. So let's limit our discussion till here, and we will continue after a short break. So let's continue our discussion. So we'll now look into the training pipeline. I think we had covered data pipeline, data collection pipeline, feature pipeline, and then training pipeline. Just a recap: data pipeline, data collection. Just a recap of the architecture here. This is how the architecture looks like. And then you have a feature pipeline and then training pipeline. The training pipeline consumes instruct datasets from the feature store. So yesterday we learned that instruct dataset could have some inbuilt prompts, could have some features stored in it. From the feature store, fine-tunes an LLM with it and stores the tuned LLM weights in a model registry. More concretely, when a new instruct dataset is available in the logic feature store, we will trigger the training pipeline, consume the artifact, and fine-tune the LLM. In the initial stages, the data science team owns the step. They run multiple experiments to find the best model and hyperparameters for the job, either through automatic hyperparameter tuning or manually to compare and pick the best set of hyperparameters. We will use an experiment tracker to log everything of value and compare it with experiments. Ultimately, they will pick the best hyperparameters and fine-tuned LLM and propose it as the LLM production candidate. The proposed LLM is then stored in the model registry after the experimentation phase is over. We store and reuse the best hyperparameters found to eliminate the manual restrictions of the processes. Now we can completely automate the training process known as continuous training. So let's look at the training pipeline here. So this is the training pipeline. So it gets data from instruct dataset. again, which will have the prompt, the features. This is also known as feature store. And then whenever a new data point comes in, this pipeline is triggered. And the end goal of this pipeline is to continuously train the models and try to find out the best LLM model. So that's the main function. Let's go through these steps once again. The training pipeline consumes the data from the feature store, fine-tunes an LLM with it, and stores the tuned LLM weights in a model registry. So let's break down these two sentences. And we'll have to do Gemini on this. So let's open the Gemini window, which we have been doing till now. So what does fine tuning an LLM mean? And what's the output of what's the output when a model is fine tuned? Fine tuning is like taking a brilliant student with general knowledge and giving them specialized training in a specific field. Again, I'll rub the analogies with the real world, like taking a brilliant student with general knowledge and giving them starting point. You begin with a pre-trained LLM. This model has already been trained on a massive amount of general text data. Specialized knowledge fine-tuning involves further training this pre-trained model on a smaller cavalcade dataset related to a particular task or domain. This could be anything from writing different kinds of creative content, answering questions in a specific style, analyzing sentiments. How does it work? During finding the model's internal parameters, think of them as knobs and dials, are slightly adjusted to better capture the patterns and nuances of the new data. This process allows the model to adapt to a specific style or tone, improve accuracy, reduce unwanted bias. The output is a modeled version of the original. This new model is now better equipped to handle this specific task or domain. It was fine-tuned when it retains the general knowledge from its pre-training but has gained specialized expertise. Analogy time. Imagine a chef who is already skilled in basic cooking technique. Fine-tuning is like sending the chef to specialize in Italian cuisine. They still know how to chop vegetables and use a stove, but now they have in-depth knowledge of Italian ingredients, recipes, and cooking styles. So this is indeed a good example. So let's come back to the book. The training pipeline consumes struct data sets and store the tuned LLM weights in a model registry. So there might be some weights associated with the pre-trained model, but once you fine-tune with the new data, some of these weights might be adjusted, and then you store those in a model registry. More concretely, when a new instruct dataset is available in the logical feature store, we will trigger the training pipeline, consume the artifact, and fine-tune the LLM. So I did not get this new construct dataset is available part. What does it mean? Does it essentially mean whenever a new data point is received or new data is received? When new data is received, maybe some new features might be created. And when you create new features, that is where a new instruct data set is created. So maybe let's try to Gemini it. What does new data set instruct mean with respect to below? Let's describe a workflow for automatically fine-tuning instructed this refrigerator specific design for instruction writer story desired output logical feature store. This is a centralized repository of trigger the training pipeline. Imagine you have a robot that can understand basic commands. Whenever you have a new set of instructions for the robot, you put those instructions in a special box. This automatically starts a process. Again, this analogy comes in handy. So indeed, what would be stored in this instruct dataset is like your prompts and the desired output. So whenever you have a new set, the pipeline will be triggered. So that not necessarily mean that the new data will be received. It's to do with the instruct. Let's look at the next paragraph. In the initial stage, the data science team owns the step. They run multiple experiments to find the best model and hyperparameters for the job, either through automatic hyperparameter tuning or manually to compare and pick the best set of hyperparameters. We'll use an experiment tracker to log everything of value and compare it with experiments. So there are 2 points here. We learned that we will be, fine tuning the LLM so that it becomes more effective. But it did not say that there would be, different LLMs. Although we read, I think, in one of the sections in this book previously that we would be using 4 or 5 models. Maybe what the authors are trying to say here is that we will be training those models, and based on the output that they're generating, so there should be a benchmark which could be used to judge which model is performing better, and that model will be selected along with the fine tuning. So there are two things that are going on. For the job, find the hyperparameters. So let's see what are hyperparameters. Hyperparameter setting that you adjust on the machine and how it works in the context of an. They are variables that govern the training process itself. They are not learned from the data but rather set by the people designing and training the model. Here is a simple analogy. Imagine you are baking a cake. You have a recipe, ingredients, and an oven. Hyperparameters are like the oven settings, how high temperature, baking time. Similarly, in LLMs, hyper influence how the models learn from the data and its final performance. Learning rates, batch size, these are some of the characteristics. Choosing the right mechanism in the ready, slow training, overfitting, underfitting. So hyperparameters is something that is defined by the data science team. So that is one of the takeaways. Finding the best hyperparameters, finding the optimal hyperparameter setting is often an experimental process involving techniques like grid search, systematically trying different combinations of hyperparameters, random search, Bayesian optimization. Understanding hyperparameters is crucial for anyone working with LLMs, as they play a key role in achieving the desired performance and achieve efficiency from these powerful models. So the takeaway is the hyperparameter is something that defined by the team who is working on ML, either through automatic hyperparameter or manually to compare and pick. So there could be two ways to train a hyperparameter, or define the hyperparameters. So that there could be two ways to define the hyperparameters. You could either do it manually or you could do it using automatic hyperparameter tuning. The testing pipeline is triggered for a so once you have so for every experiment that goes on in training the LLM and generating the output, that would be logged somewhere so that you can have a track of what are these experiments that are performed. And based on those logs, I think a decision will be made to pick the best LLM. Whether this happens automatically and there is a manual intervention involved, I don't know, but we'll look into it. After the hyper experimentation phase is over, we store and reuse the hyperparameters found. Now we can completely automate the training known as continuous training. The proposed LLM is then stored in the model registry. So once you have the LLM finalized, you will then store it in the model registry after the experimentation phase is over. We store and reuse the best hyperparameters found to eliminate the manual restrictions of the processes. So there are a lot of terminologies being thrown around here. One is features. Features are derived from data. Then you have feature store, which gets stored in features are stored in the feature store. Then you have parameters or weights. These are like the probabilities or in the context of neural networks. These are like the weights or the probabilities, and maybe we can simplify it that how a particular node is connected to other nodes. And then we have hyperparameters. These are defined by the team, not within LLM or data. So these are the terms we have to keep in mind. And once everything is finalized, you have the LLM model registered in model registry, you store the hyperparameter. Then we can say that the training pipeline is completed. Now we can completely automate the training pipeline with continuous training. The testing pipeline is triggered for a more detailed analysis than fine tuning. Do we have a testing pipeline here? This is the training pipeline. Experiment tracker, test, LLM candidate, model registry. Let's read. Testing pipeline is triggered for a more detailed analysis than during fine-tuning. Before pushing a new model to production, assessing it against a stricter set of tests is critical to see the latest candidate is better than what is currently in production. In this step, if the step passes, the model is ultimately tagged as accepted and deployed to the production inference pipeline. Even if in a fully automated ML system, it is recommended to have a manual step before accepting a new production model. It is like pushing the red button before a significant action with high consequences. Thus, at this stage, an expert looks at the report generated by testing component. If everything looks good, it approves the model and the automation can continue. So, where is this testing pipeline? How come this testing pipeline or how the testing pipeline is invoked? That is something a question for me. So, this is a training pipeline. Here on LLM experiments, then the experiments are stored in experiment tracker. Then you pick, maybe that is the training pipeline. You pick the best model out of the experiments that you've done. And then based on whatever the best model is, that goes into the model registry. And then this is the manual step that they are talking about before deploying it to production. There should be human loop, a person or a group of person that should be able to look at the reports generated by the new model, and a decision needs to be taken whether this new model worth deploying it to production or not. All the client queries enrich prompts using Okay, I think we went a little ahead. Pipeline, the training testing pipeline. Okay, it is like we read that. The particularities of this component will be on LLM aspects such as the following. How do you implement an LLM agnostic pipeline? What fine-tuning techniques you should. How do you scale the fine-tuning algorithm and LLM dataset of various sizes? How do you pick an LLM production candidate from multiple experiments? How do you test the. By the end of this pick, you will know to answer all these questions. Yeah, I also had these questions in mind, like how do you train multiple models and then try to benchmark those. So basically, all these decisions will be made during training pipeline. So which means that training pipeline, as would you know, common sense is that training pipeline is the important pipeline in ML architectures. One last aspect we want to clarify is CTL motor design allows us to quickly leverage an ML orchestrator or to schedule and trigger different continuous. What does CT stand for? Continuous training. For example, we can schedule the data collection pipeline to crawl data every week. Then we can trigger the feature pipeline when the new data is available in the data warehouse and the training pipeline when new instruction datasets are available. Cool. So they're saying that this all can be, orchestrated. By CT, they by CT they mean continuous training. So you have continuous data collection, continuous feature generation, and then continuous training. We're down to the last one, which is inference pipeline. The inference pipeline is the last piece of the puzzle. It is connected to the model registry and logical locate loads a fine-tuned ML LLM model from the model registry and from the logical registry. This is the vector DB for RAG. It takes in client requests through REST APIs queries. It uses the fine-tuned LLM and access to the vector DB to carry out RAG and answer the queries. All the client queries enriched with prompts using RAG and generated answers are sent to prompt monitoring system to analyze, debug, and better understand the system. Based on specific, the monitoring system can trigger alarms to take actions either manually or automatically. At the inference level, this component follows exactly the FTI architecture, but when zooming in, we can observe unique characteristics of an LLM and a retrieval client used to do vector search for RAG prompt templates, map user queries, and extra special tools for prompt monitoring. Yeah, we covered a lot of sentences here, but let's see what it does. So inference pipeline should be moved when, for example, I'm writing in this contextual window. So that would be that would so when you type in any prompt, API call is made to the model. That API call will also include your data because it might have to look up on that, and then based on and then the LLM uses the model from the model registry, and there could be prompt and system monitoring, where the prompts should be saved. So once you have the LLM model using the model from model registry, the output of that is then served to the person who was making the call. The last page is connected to the image. It loads a fine-tuned LLM from the model. Okay. It takes in transit to a REST API, uses a fine-tuned model access to okay. All the queries with prompt and advances are sent to the prompt monitoring system to analyze pattern based on this in the monitoring system can trigger alarms to take. At the interface level, this component follows exactly the but when zooming in, we can observe unique characteristics of an LLM and RAG system. A retrieval client used to do vector search, prompt templates used to map user queries and external information to LLM inputs, special tools for prompt engine monitoring. So apart from the FTI components that you see in this FTI architecture, the authors are saying there are some other pieces as well, like this RAG data and prompt and system monitoring or retrieval client. So these are the systems or functionalities that have to be called out separately. Final thoughts on the FTA design, and we don't have to be highly rigid about the FTA pattern. It is a tool used to clarify. For example, instead of using a dedicated feature store just because that is how it is done in the system, it is yeah. So they're saying we don't have to go by the book. So here they use VectorDB to store feature store. What was important to focus on properties. Ultimately, we'll explain the computing requirements of each component briefly. The data collection and feature pipeline are mostly CPU-based and do not require powerful actions. The training pipeline requires powerful GPU-based machines that could load on LLM and fine-tune it. The inference pipeline is somewhere in the middle, still needs a powerful machine but is less compute intensive than the training stuff. However, it must be tested carefully as the inference pipeline directly inferences with the user. Thus, we want the latency to be within the required parameters. However, using the FTA is not an issue. You can pick the proper computing requirements for each component. So now I think they're talking about the compute infrastructure. The data pipelines can run on CPUs. Training pipeline would require feature pipeline can also run on CPU. Training pipeline would require GPU, and then inference would require a combination of GPU and CPU depending upon how complex the prompt is or how data heavy the prompt is. Ultimately, explain the computing which requires the data. Okay. Each pipeline will be scaled differently. The data and feature pipeline will be scaled horizontally based on the CPU and RAM based. The training will be scaled vertically by adding more GPUs. The inference pipeline will be scaled horizontally based on the number of client requests. So what it means is if it is horizontally, then you need multiple machines. If it is vertically, that means only one machine can do the job for you. Okay, to conclude, the presented LLM checks all the technical requirements listed at the beginning of the section. It processes the data as requested, and the training is modular and can be quickly adapted to different LLMs, datasets, or fine-tuning techniques. The inference pipeline supports RAG and is exposed as a RAG API. Knowledge system supports dataset and model versioning. So here you go, guys. This completes our chapter 1 of this LLM engineering book. Now we'll be moving to a different book for our book reading series. But personally, I would like to continue with this book because I might be able to do some demos. And then instead of just going through and reading the pages of the books, we can look at the demos. Now, hopefully, I can try to do that for you. Let's see how far we can go. So, thank you again for watching this lengthy video. This was one of its kind. I gained a lot, and I hope you understood few concepts, terminologies. Self-study would be required, so I would encourage you to do that. And we'll meet soon in our next video. Till then, take good care of yourself, guys. Bye.